All right, now we come to the last part, advanced modeling approaches. This approaches can be intimidating and challenging, but I hope they are also rewarding. At least I have put much passion into it. First, let's consider cross-trial variability. There are two types of samples in AFNI. One is about number of subjects. So the reason we in an experiment to recruit a number of subjects is basically we use those subjects as representatives for a hypothetical population. So in the end, we want to generalize from those specific subjects to a hypothetical population. So in the model, each subject there associated with each subject, there's a term in the model. So there's a position for each subject. That means the cross-subject variation is explicitly accounted for. So we can that helps us to achieve the generalizability. That's why we sometimes we call it random effects model. That's in the early days of AFNI data analysis, there term or the modern approach called the fixed effect analysis. In that case, the assumption was to assume all the subjects share exactly the same brain response at each brain region. But that nowadays, that's just considered outdated. That means if you adopt that approach, your paper would be definitely rejected. How about the other sample size, trials? It's exactly the same reason an investigator to adopt a number of trials. Again, the reason is to choose a specific number of trials to as a representative for a hypothetical condition in abstract sense. For example, if you want to study happy face, you would choose, for example, 20 number different faces, smiley faces. Those faces are smiling, but they have different styles of smiling, right? They may have different air style. They may have some each face maybe the person is at a different age. So there are a lot of variations too. But what do we do typically in FMI? At the subject level, the model is there's only one regressor created for all the trials. That means the underlying assumption is all the trials share exactly the same brain response. That's equivalent to fixed effects modeling for cross-subject variability. But would you get your paper get rejected for this reason? No. But is this troubling? Of course, because you assume there's no cross-trial variability. But what's the consequences with that assumption? Well, the first problem is it's not legitimate to generalize from those specific faces to an abstract face. So, but that's the investigator usually wants to make that generalization. So that's one problem. The other problem is the potential distortion of the effects and the statistical evidence as well. So those two aspects are troubling. Can we do better? Of course. We have been doing that for subjects for a long time. We can do the same thing for those trials. So what do? We model each trial separately at the subject level. That in doing that, we are not ignoring cross trial variability. So when we come to the population level, then each trial, there's a associated effect with that trial, exactly the same way we do with subject cross-subject variability. So, but the modeling, of course, it's more challenging and it takes more time to run, but there's a way to do it. There's a new program called 3D RMER that can be adopted to handle this kind of situation. Basically, you have two random effects that crossed in the sense that they have their own one-matrix terms. So it's as long as you are willing to investigate some effort and time, and then your model would be more legitimate. So that's one advanced approach to handle cross-trial variability. The second modeling approach I want to discuss is called intersubject correlation. This is specific for one type of AFNI scanning. It's called naturalistic scanning. It's a niche part of analysis and study. Some people consider the typical task-related AFNI a little bit too artificial in the sense that they are far from real life, right? So like look at the smiley faces; those faces are still, right? So they're not animate, and there's other than just the face, there's no further, rich information. So the people do different kinds of experiment. They put the subject in scanner, let them watch movies, or listen to a speech or music. So that kind of, not exactly real life, but at least it's close enough. So you don't have a specific task other than just continuously watching or listening. So suppose you watch for example, 50 minutes of clip, then you just have those 50 minutes data. How do we analyze it? There are many ways, of course, but here I focus on one particular approach. People call it intersubject correlation. So suppose you have 5 subjects, okay? Then you calculate the correlation between each pair of subjects. So 5 subjects, we would end up with 5 times 4 divided by 2. That's 10 subjects. That's on the right-hand side of this slide, you can see. So with 5 subjects, we have 10 intersubject correlation pairs, right? So at each voxel or each region, we have 10 correlation values. So if we put those 10, then formulate the 10 by 10 matrix, that will give us some idea about their relationships. So some of the pairwise values are related, some of them are not. That's why you can see in the matrix some of zeros, some of them are non-zeros. The diagonals are one, of course, they're self-correlated. But let's look at 2 cases. One, the cyan color. So that's 0. Why that one is 0? That's because we have 2 pair, two pairwise intersubject correlation values. One is this one, that's between subject 1 and 4. The other one is between subject 2 and 3. So those 2 pairs, there's no common subjects, right? So they don't share common subject. So that's why we can reasonably assume they are independent with each other. So we can put we can assign a 0 correlation value between those 2 pairs. In contrast, the other pair, this between subject 2 and 3 versus the other one between 3 and 5, they do share one common subject, subject number 3. So in that case, we should assign a non-zero correlation value there. So in the end, we have this complex correlation matrix pattern. So how to handle that? It looks, is there a pattern? Of course there is, but what is the pattern? I don't know. I can even name what the pattern is. There is a pattern, of course, that's based on the relationships among those intersubject correlation values. But how to handle it? Well, that's the magic model. It's called the linear mixed effects model. We can partition each subject pair into separate components. So we can disentangle the relationship, put them into a hierarchical structure that is scaffold would allow us to characterize the intricate relationships among those intersubject correlation pairs. So there's a program associated with it. It's called 3DISC. There's also 3 papers actually are associated with this type of data analysis. That's for intersubject correlation. The next topic, test-retest reliability. Some of you may be familiar with the concept of intra-class correlation. Well, the origin of this concept probably started with some people call it inter-rater reliability. So you have a list of raters. They judge the performance of some, athletes or something, and then give them a score. Each of them their performance score. So those raters, do they the assessment consistent across those raters? So that's the question. Well, when we apply that approach to AFNI, we would have a situation like this. Suppose we have two conditions, right? So we put a group of subjects in the scanner, then perform those two tasks. Then we repeat that. I mean, after, for example, some period of time, like 3 weeks, for example, we do it again, exactly the same conditions and same subjects. So we just repeat it twice. That's simple the case. So we want to check how reliable or how consistent of those subjects between the two repetitions, right? So that's a simple like that. We're not going to run ANOVA to get the population effects. That's not the concern for this context. We want to show the consistency. But how to measure that consistency? Well, some people call this kind of reliability about individual differences, because it's not the population level effects we care about. Instead, it's each subject is differences. So, for example, subject A may respond stronger than the population average during the first round. So, if the AFNI is reliable, we would expect during the second round that subject A would also respond higher than the population average. On the other hand, another subject B, during the first round, we suppose this subject responded lower than the population average. So if it's consistent, reliable, we would expect the second round, the subject B would also respond lower. So that's sort of some kind of a synchronization. That the extent or the degree of synchronization is what people call intra-class correlation. So that measures that metric basically gives us some sense about the reliability. So that approach, in the old days, people use ANOVA. They could use two-way, either random effects, both factors are random effects factors. I mean, we have two factors here. One is the two conditions, right? The other one is the repetitions. And also, of course, we have subjects. So in the old days, people use ANOVA, but nowadays we don't have to. I mean, it's even more adaptive and flexible to use linear mixed effects model approach. So there's a program associated with this the linear mixed effects model methodology. It's called 3D ICC. But there's a catch here. If you follow the literature, the reliability is really poor. Not just for AFNI, even for in psychology, like the famous tasks like Stroop or flanker tasks, they show really poor intra-class correlation values. For example, Stroop effect, the recent study, they showed the ICC value is only around 0.05. In AFNI, I mean, most of the ICC values are less than 0.4. That's really disappointing, right? So, I mean, that's why people feel a little bit doubtful about the reliability of AFNI. Of course, AFNI are not flawless, right? So it's understandable. People have some doubtful attitude about the approach, but is really that low, even for behavior data like reaction time for those popular tasks like Stroop and flanker effects, right? So there are recent development that tackles the problem about the traditional ICC. So this the problem actually is associated with the problem, the typical FMI that ignores quasi-trial variability. That's exactly the same problem with the traditional interclass correlation. If you pay attention, close attention to the specific model, there's no such a term for trials. The reason is because the classical inter-rater variability, because in that case, those judges, they give the performance scores. There's no multiple trials. Each performance, there's just one performance per subject, for example. There's no the notion of trials. But for FMI or for even for psychology, those Stroop or flanker tasks, usually we have many trials. It can be tens or even hundreds of trials. So that brings up a problem because basically the quasi-trial variability is not accounted for. That's the problem. So that's basically shares the same problem with the typical FMI methodology. Once we realize the problem, then we can do a better job. So under this new framework, we specifically model the trial level effects. So in FMI, at the subject level, we would create one regressor per trial. Then that would allow us to formulate a more reasonable approach. So for Hopper-Fox-wise analysis, I'm going to implement the option in 3D MER to handle the Hopper methodology that can incorporate trial level effects. My current experience is this approach works for simple effects, but for contrasts, that can be problematic. There's a reason for that failure. That's basically it's numerically we have the problem, convergence problem, or either singularity problem, because the correlation value may get close to the boundary, like -1 or 1. Once you get close to that boundary, the solver may fail to and gets trapped, cannot get out of it. Then you get correlation value of 1 or -1. That's usually that's not reasonable. I mean, it's close to 1, but that doesn't mean it has to be exactly 1. So there's a better approach. That's based on multi-level modeling. In that approach, well, currently we can only handle at the regional level. So each RI, we can model it separately. So there's a program which I'm going to create soon. Probably I will call it TRR, standing for Test-retest reliability. That approach will perform much better. So my current testing shows that you could reach Test-retest reliability up to, 0.9 or even close to 1. So that's pretty, even I was surprised, pretty stunning. So there's hope we can achieve better, more accurate estimate for reliability. That's can be important from many perspectives. Like people can use FMI as biomarkers, right? So that's something hopefully will gain some traction for this new model. Lastly, I'm going to talk about the handling multiplicity problem. Why do we have this multiplicity problem? Well, some people call it multiple comparison problem. Well, the popular approach in FMI is massively univariate analysis, right? So we have voxels, we have regions, we have nodes on surface. This approach treats every voxel or node or region as an isolated entity. What do I mean by isolated entity? Well, what do we do? I mean, you suppose you have, for example, 100,000 voxels. All those voxels, they don't share any common information. Each voxel is analyzed separately. Each voxel has a separate model, right? So 200,000 voxels, you have 200,000 models. But that's immediately under the traditional statistic framework, you have this multiple comparison issue, right? This approach has been adopted over the whole history of neural imaging, right? And it's intuitive, right? That means everybody understands the approach. It's straightforward, and all the tools are built for this purpose. But the big problem is how to handle the multiple comparison problem, right? So in the field, currently there are two recognized and pretty much popularly adopted approaches to handle this. The idea is to use the labeling voxels as leverage, right? So the intuition is that, I mean, if we just pure noise, that you may have some voxels that reach so-called significance level, but those voxels tend to be sporadic, isolated. It's difficult if we just pure noise. They would be difficult to form a cluster, right? So they would be difficult to get together. That's the idea. So with that intuition, there are two basic approaches. One is called the cluster-based adjustment. So in AFNI, if we use 3D T-test plus plus, automatically there's an option embedded with that program. It's called a crossing. So that if we use that option directly as part of the analytic process, then in the end you would get those survived clusters. The other scenarios, I mean, 3 T-test plus plus basically use that for T-test or simple ANOVA or ANCOVA. But you have sophisticated designs. You may have to use 3D MVM, 3D ME, 3D MER. In that case, there's no option directly embedded with those programs. So when you run those programs, then you get the results. Then you have to use a separate program, added-on approach. So you can use 3D crossing. You basically use Monte Carlo simulations to assume there's random noise in the data. Then with this roughly the same spatial relatedness with your real data, then to say if you could by chance get some minimum clusters. So they use that cluster threshold as a way to control the overall false positive rate. So that's the cluster-based approach. The other approach is called the permutation-based adjustment. In AFNI, that's only available in 3D T-test plus, embedded that with an option called the E-tag. So the idea is also relatively intuitive. I usually use a mountain as an example to describe and understand the approach. So the cluster approach, basically you only consider the spatial part. So you either survive once your real cluster is above that threshold, then you get the survived one. Otherwise, you lose, right? So the permutation-based approach is sort of a little bit slightly better comprehensive in the sense you combine two pieces of information. One is about the spatial extent. The other one, you get the subtle information about the statistic evidence, right? So, I mean, some clusters they may be small, but their evidence can be strong. So you combine those two pieces of information. Another cluster may be large, the statistic evidence may be weak. So you combine, then you leverage. So that's a little bit more balanced approach. So that's the traditional way to handle multiplicity. But there are many problems. I mean, I can go on and on forever. But let's just focus on a few. with this the traditional approach. What's wrong with the traditional approach? First of all, there's this big problem called the overfitting. Why? What is overfitting? Well, when we adopt this massively univariate approach, we assume all those spatial units are unrelated, right? So that's why we have each voxel or each node or each region has a unique model, right? So that is, there's an underlying assumption with that approach. The assumption people don't see it or don't recognize it. That assumption is all those spatial units, they don't share any information. That assumption is they're uniformly distributed. On the right-hand side at the top, you see that they are flat line, the blue line. That's the assumption. So basically, you have a prior. From a Bayesian perspective, that prior is you have no knowledge about the distribution of those voxels or nodes or regions. Is that a reasonable assumption? Do you truly believe there's no common information among those spatial units? No, that's not true. I think you would agree if you plot out the distribution of those spatial units, you would more likely to say something like the bottom on the right-hand side. We do have that prior knowledge. That's exactly the same assumption and same understanding. We recruit many subjects. We design many trials for each task. The reason is we assume those subjects follow a Gaussian distribution. We don't assume all the subjects are like a flat line, their brain response going from minus infinity to positive infinity. No, that's not what we do. We do assign a prior to those subjects. That prior is Gaussian distribution. We don't say or we don't impose how those subjects are concentrated. We just say that they follow Gaussian distribution. That's good enough. That prior assumption would have a big impact. So that's with this the massive unit approach. The underlying assumption with that uniform distribution, the big problem is it's overfitting and we waste a lot of information. That's why we have this heavy penalty. That's why you may experience the problem of getting your clusters to survive the dichotomization process. That penalty can be heavy and very wasteful. We design experiment, recruit so many subjects, spending hours scanning, analyzing data, writing up. In the end, so many clusters are wasted because of this massive unitary approach with the underlying assumption of a uniform distribution. And in the end, another big problem is dichotomization. Some people call it dichotomania, because in the end, you only see those clusters, those lucky clusters that survive the so-called cluster threshold or the combination of spatial extent and statistical evidence intensity. So regardless of what approaches you adopt, in the end, you only see those lucky ones. Anything under the sea level, even if it's island or some rocks still underwater, you pretend they are all water. They are in the wasteland. So there are too much information wasted, and you would discriminate those anatomical small regions because they are intrinsically disadvantages. Because since they are small, they are difficult to form big clusters. Even if their statistical evidence, the intensity can be high, but intrinsically they're small, right? Anatomically small. So you put them in a disadvantageous place. So that's a discrimination. Also, the traditional multiple testing adjustments methods are vulnerable to manipulations, right? I mean, I don't want to say much. There's famous small volume correction. I mean, you can do magic about it, but that's that's maybe a sugar-coated p-hiking, right? So you can manipulate the amount of data you want to focus on. You can keep shrinking the amount of data. Of course, in the end, you would get your cluster to survive. That's that rigid, or is that too much arbitrariness, right? So anyway, let's talk about alternative approaches, hopefully better, avoid so many problems associated with traditional massive Euler approach combined with multiple testing adjustment. So let's see what can we do better. Well, let's focus on a list of regions. Those regions you can predefine from different perspectives. You can define based on literature, right? So, or you can use half of the data to design those regions, then use the other half to run the region-based analysis. Anyway, so whole brain voxel-wise cannot be done because of the computation cost, but also because of other reasons, which I will briefly touch a little bit later. So suppose you choose some number of regions. In this case, on the right side, we have, in this case, 22 regions. With those regions, we create one model instead of 22 separated models. So we incorporate all those regions into one. In doing so, automatically, there's no multiplicity issue anymore, right? Because there's only one model. With that one model, then we get everything out of that model. That's why you see on the right-hand side, all the results are presented. So all the problems I mentioned on the previous slide are not here anymore, right? So there's no multiplicity issue, first of all. Then there's no dichotomization. We present all the results, regardless of their statistical strength, weak or strong. Everything here is in front of everybody's eye in the paper, right? So you don't have to dichotomize. You can choose whatever threshold or you consider as a strong or weak or moderate evidence. And that will be helpful for everybody because we don't have at least one less problem for reproducibility because we present the full results. And later on, people can use whatever evidence strength to make their own judgment. And for meta-analysis, you can use all the information regardless of their evidence strength. So, and no dichotomization, no discrimination against the small regions. Why? Why no discrimination? Well, everybody is putting on the equal footing, right? Regardless of their region size, we judge them based on their effect strength and statistical evidence. So, and there's not much room for arbitrariness. You don't need to manipulate the data because, of course, you can vary the number of regions, but that variability, because the model is adaptive. You have put in more regions, then the prior distribution, the Gaussian distribution, would automatically to adapt to the different number of regions. So the program is called RBA, standing for region-based analysis. So it's already available for a couple of years already. So that's for region-based approach. The next one is matrix-based analysis. Suppose you have you define some number of regions, then you get the correlation values or some measures among all those regions. So you end up with a matrix per subject. So in this illustrative example, we have 5 regions forming a matrix 5 by 5, that's symmetric. So we have 10 off-diagonal values. So that's why on the right-hand side, you see a 10 by 10 matrix that characterizes the relationships among those matrix elements. Similar to the intersubject correlation matrix, we have this complex pattern, right? Some of them correlated, some of them are not, right? So I don't want to repeat what I mentioned before. So we have this complex pattern, but how to handle this? Well, with the Bayesian approach, basically we build one model. Unlike the traditional approach, when they deal with the matrix data, they analyze each matrix element separately. So in this case, we have five regions. So we have 10 region pairs. So 10 by 10, right? So that we have 45 matrix elements. So traditional approach, for example, network-based analysis. With that approach, you basically build 45, in this case, 45 separate models. Again, in the end, you have this multiplicity issue. How to deal with that? Different ways. Permutation tests. There are a couple of variations, but that's we already talked about. But let's say what can we do with the Bayesian multi-level modeling? We apply to this particular data set with 16 regions. First of all, we don't have multiplicity issue because we only have one model. On the left-hand side, we see the results, full results, low thresholding. Everything is presented. You can highlight some region pairs based on the strength, but you don't have to hide the rest. So that's the beauty of part of this approach. So everything is in front of your eyes. On the right-hand side, we show the 6 regions, their importance, some importance measure. So it's similar to graph theory. You have this, they have this concept of hops, right? So here again, with 16 regions, we show all their statistical evidence and their effective magnitude. And you can judge yourself about their strength. So this is the matrix-based approach. I think this is the last slide I have. And also this wraps up the population-level modeling talk. If you have reached this point, congratulations. Let me know if you have any questions, suggestions, feedback. All right. Thank you. Bye.